right? These are straight lines. And we're going to talk about something eventually where it comes to a point like this as opposed to being nice and smooth. Okay, these are two different instances. Something nice and smooth is its own function. But really, when it has these jagged edges or these corners, it's actually kind of a piecewise function. So all they're saying is from here on, when we're plugging in values, then it's just 1 over x, right up 1 over 1. So then that's why they're saying this. Okay, and so then over on this side, right, that's a negative slope. Is that okay? And that's all they're saying with that. All right, so pretty straightforward, I guess, right? No problems, right? You're just plugging in numbers, no big deal, yeah.
Can you do like 45?
Sure. Okay. I'm going to kind of talk it through, but I'm not going to do I'm not going to really break it all down. Do you want me to open a window for you guys? All right, so the whole idea is that theorem 2.4, limits of polynomial and rational functions. They're just saying you can plug in A. And when we used our limit laws, we were just breaking it down into littler things just to show that that was true. There's no real reason for you to break this down. Now, in the long run, we might have bigger things. And again, limits roll into derivatives. And so it may be nice to break things down later on, okay? But something like this, all we're saying is if this is our function, right, then all we're really finding is this. And so then, you're just going to plug it all the way in. Yeah, you're totally welcome to apply as many limit laws as you feel like you need, but, there's no need that we use that to prove that this is true. So now you just go with it. Okay. Anything else from that? All right. So let's do a couple homework problems. So we're going to just start on 39. All right, so rational function, right? So by that same theorem as the polynomial one, it says we can just plug these in. But what ends up happening? You have a thing, right? So this is something that may happen. What do you notice about these two functions, though, right? One on top of the other. If you do what? Yeah, so if you factor first. So I'm going to say this. Try not to get sloppy with what you're writing, okay? I know it's easy to not rewrite the limit as x approaches 1, but I suggest that you do, okay? Because you're going to end up losing stuff later. Maybe now it's not a big deal. But I do suggest that you rewrite everything and not get carried away, because eventually things will start disappearing, and I don't want you to get confused later on. So there's where the x minus 1s disappear. So now we just have the limit as x approaches 1 of x plus 1. And so now we can say that that's 2. So if this situation happens, maybe factoring can take care of it for you. Is that all right? And, we talked about this real briefly. This function, if we graphed it, looks fairly intimidating, but it's really just a straight line because of this thing that gets canceled. Okay, Okay, and I mentioned this before. If something gets canceled, it's most likely there's a hole there, at least with what we're looking at. Okay, and so then if you have it graphed, and I do suggest that you play along and graph them and look at them too. You can see that the y value is 2 right there. So is that okay? So I think the next one we should look at is 47. I don't want to take your phone away. And, you know, totally while you're learning this, it's legitimate to type this in your calculator and take a look at it and make sure you're thinking straight. Now, these are totally problems that would be on the non-calculator part. And next week we'll be ready for the test on this. And I do have a calculator and non-calculator part, and we got some AP problems that we're going to do also. So those 3 days we'll have 3 different test days on that. The one is super small, so I have to work out how to do it. Maybe we'll have 4, I don't know. Okay, so again, what's the problem here? 0 in the denominator, right? We'd love to just plug it in, but we cannot. So, a little different, right? So we can't square the whole thing because then you're changing the function. So something hopefully reminds you when you see a radical in a fraction, hopefully that makes you think to do something.
You get a simplify the top.
By doing what?
Multiply by the square root of x minus 3.
So we can try that.
Or like make radical x squared.
So let's do what he's saying first. So let's say we did that. So just hold on for a second. What would happen up here in the numerator? So I guess right, we basically just have what I just wrote, right? Would that help us? Would we eliminate the 0 from being in the denominator? Okay, so he's on the right track though. We would FOIL that out. I guess maybe just looking at it. He's very, very close. Okay, we're getting closer. So if we tried x plus 9, right, then down in the denominator we'd have x squared minus 81. But then when we plug in 9, we still have the same problem. But we're getting closer. There's a fancy word for it. It begins with a C. Yeah, we can do the conjugate. You kind of try to do the conjugate because you're used to doing just the denominator, but that didn't do us any good. So we actually need a conjugate with the numerator now. At least I assume this is what this problem's about. Okay, and I didn't FOIL out that other one because I knew it wasn't going to work, but right, there's really no reason to FOIL the numerator. So I'm going to kind of leave it like that as of right now. And so I would suggest, because I've done a lot of these problems, don't FOIL unless you need to. Right? Don't waste your time doing something, because all we're going to do is plug in a value up here, and so who cares if it's all the way out. But down in the denominator, let's see what happens. Right, we got an x and the square root of x, and then we got a plus of 3x and minus a 9 square root of x minus 27. Okay, and again, we got to do that because if we don't FOIL the denominator, we're still going to have a 0 out front. But now that we FOIL it, let's see what happens, right? We have 9 times 3, is that okay? plus 27. No, it still didn't work. Oh, what's this problem? What's that? It's spoiling. Maybe this is another factoring one. This might be another factoring one. I didn't want to do a factoring one.
You have to like change the -3 to like radical x minus radical 9 and something like that.
Yeah. Okay, so let me finish this because like this is something that you're gonna have to try. So right, then we get this again, minus 27. So we actually still get 0 down there. This is something that you guys need to do. I was hoping I grabbed the right one. So essentially, those are our two options. So we tried to do the conjugate of the numerator. It didn't work. The conjugate of the denominator doesn't work. It's in the problem that it's this section that's supposed to work. So we got to factor this thing. How can we factor this thing? I saw radical. I thought it was that one. We'll do another one of these, but. So how can we try to factor one of these? If I read it like this, maybe that would help. Does that give you an idea of what we can factor? So right, everyone, that factors, right? So what do you notice that happens to the 4? And so that was by what? Square rooting. What happens to the exponent of the x's? They go to half, right? So then so you should be factoring this one. Yeah. All right, so that's a dirty trick, right? Okay, so now we can actually cancel. And I'm running out of room here. But so now we have the limit as x approaches 9 of 1 over. That's ugly. Right, so then it becomes 1/6. Is that okay? Right, because that's just a square root. So the square root of 9, you can see my finger. So the square root of 9 is 3 plus 3, so for 6.
Also -3 plus 3.
Well, these two cancel though. Like this is basically the same problem again. These two end up canceling, right?
Yeah, but like the square root of 9 would also be negative. Not just positive. So it would be -3 plus 3.
Okay, so when you are doing an equation and you want to take a square root to solve, then you need a positive and negative. This is just like a statement of the square root of 9. And that gets taken care of by this thing up here. My finger shows up. Right? That's where your negative came about. Okay? So, that's how you're going to have to do some of these problems, though. Right? Your options are going to be to factor and cancel, and then do the conjugate. And so, like, I was just looking like, oh, there's a good example problem and you do have to do the conjugate with the numerator occasionally. And so I'm just like, oh, this must be a conjugate problem simply because I looked at the radical. But we didn't get anywhere with it. So then you got to back up and see if you can factor it.
So like, what if that was the problem we were given from the start? Like, what if we started with 1 over the square root of x plus 3? Like wouldn't that provide, like, there'd be a below that still? Yeah, something
we didn't decide to take a square root. This isn't an equation. Okay, so the negative, right, so you know, you can't, well, let's see. Basically, when you have something like this, right, it can only be 4. Oh, sorry, yeah, sorry. Come back down. Right, it can only be 4. It can't be negative 4, right? But if you have something like this, it can be both positive and negative too. Because when you square negative 2, you still get 4. So, right, so on this one, this is where you're deciding to, where's my finger? There. When you're doing this one, you're deciding that, oh, I need to, this is like kind of we talked about, like there's 2 answers here. I have to take the square root to find them, so I better get the positive and the negative. This is just like, so that's the difference between the two. All right, so should we do a conjugate one, or do you understand how the conjugate is going to work? So like if you look at 49, that's totally a conjugate problem. Well, that's probably another factoring one. Could be a fraction, could be a conjugate. 51 is probably definitely a conjugate one. Probably definitely. I mean, I could look and see. But again, I mean, this is part of the gig, right? Like, times of knowing exactly how to attack a problem are gone, right? I mean, that's when we're doing definition math, okay? So I mean, you're going to make mistakes, and if you're not making mistakes, then you're probably not doing any of the work either. So 51 is definitely a conjugate one. $49 is probably a conjugate one. I don't want to take your excitement away. All right, so that okay? All right, so flip back for a second to page 82. We just got to talk about some things, and then I'll get out of your all's way. So again, let's go through. Here, I'll even right now. Okay, we'll call it the same thing. All right, how do you do it? Oh, where is it? It's more exciting this way, Alexa, because you don't know what I'm writing. I could have written anything. In your mind, it might have been like, ooh, maybe he's writing bologna sandwich this time, because that's what they want. All right, so how do you compute a limit, right? Yeah, okay, so, right, hopefully, just plug in the value. And that works for what? Or what does it not work for? It doesn't necessarily work for rationals. Radicals, I mean, like if you're asked to find the limit of that, right? I mean, there's like nothing you can do because there's no such number. So really, the radicals. I mean, I guess they could ask you that, but I mean,
so can the limit be I or can it not?
I got a feeling that's a different calculus class. Like, right, you got to get 1, 2, 3, 4, and so we don't deal with imaginary numbers. We deal with some polar things, but I'm sure that exists. Okay, but we don't need to deal with that in Calc 1. Right, I guess this is like Calc 1 and Calc 2. So probably any of your questions like that, I'm sure someone in the history of calculus has studied that, but we don't have to, okay?
Got it.
All right, and so, right, what happened, what's our other option? Like, so if the denominator ends up being 0, then what? So, right, you gotta try two different things. Factor and cancel. Or what else? Or multiply by conjugate. And remember, right, it could be numerator or denominator. All right. And then, of course, and this kind of goes on Tim's question in a way, there's totally going to be a bunch that don't work that way either. So, right, so then, like, then we got more things that we got to learn about, okay? But as of right now, those are your really only options. Okay? So, look at page 82. Page 82. And they say, oh, it's an important limit. And so this example 7, we're going to deal a lot with exponential functions and derivatives and limits of exponential functions. And they usually talk about, and you probably can't see it on mine, but they usually talk about 2 to the x because it's an easy one to think about, but maybe it's e to the x. Those are really the only 2 that we talk about. But they're all the same, right? Later on, it'll only be e to the x, right? Not only, but more often e to the x. And so then they say, okay, you want to go to this 0.01. And then the problem ends up being that you come down here to the bottom. I know you can't really see it. But then the limit, well, let's talk about how we get there, I guess. So, right, this is, if you're looking at figure 2.19, this is like connecting the first couple sections to what we're doing now. Okay, and so how do you do limits again, like with respect, like how do limits and secant lines match up? So then you're shrinking up that secant line, the distance for that secant line, so it's a tangent line, yeah? And so that's what they're showing you over here, like, look, oh, here's the tangent line at 0, 1. And so then, right, what we're really talking about is the slope formula. And then we have this issue where, like down here, where, well, x is just 0, and so then we can't do anything about it. Now, doing a conjugate or factoring doesn't do us any good on this, is what they're telling us. And so then they're saying, okay, well, so then as of right now, and again, we'll spend a lot of time with this function. You're going to see this function quite a bit, okay? And there's a whole section that's like derivatives, again, which is basically what we're doing, slopes, okay? Where we learn how to deal with this. But as of right now, we just do it like we were learning in those first couple sections, where you're just plugging in smaller and smaller intervals, doing the slope formula, and saying, oh, look, it looks like it's going to 0.693. Is that okay? So you're going to have a couple questions on that, and we can, if we have time, we can go look at that. But we got to talk about the squeeze theorem. So read theorem 2.5 yourself. And the first paragraph, I guess, under the squeeze theorem. And definitely look at the pictures, figure 2.20, 2.21. So how many people feel like that makes sense?
If there's a line in between two lines and all went through the same point, the limit's going to be the same at that point.
Yeah, that's it. Is that all right? That's a pretty good way to describe it. Okay. So is that okay with everybody? So here's the thing with the squeeze theorem. It's kind of annoying because you're probably going to be asked about it, but like we only talk about like very rarely, and then all of a sudden they'll bring it back up, and you're like, oh yeah, what the heck is that thing? Here's what I would say is that I don't want to say never, but if we're looking actually at the theorem itself, I don't think that you're going to actually have to come up with f of x and h of x. Okay? So it's not like you're going to be asked a limit, and if you find out that you are, just tell me, because I won't repeat this lie to everyone else, but like, the way it's going to work is they're going to say, hey, look, there's this situation where we're trying to find the limit of g of x, and it so happens that everywhere that we're looking, f of x is less than g of x and h of x is bigger. So now show us what the limit of g of x is. And so then the process is to show that both h of x and f of x go to the same point, and then you say, by the squeeze theorem, I know that g of x goes to that same value also. Is that okay? What's that? Yeah, totally. Okay, and so again, if you're going for a 4 and a 5, that's the kind of thing that you have to be able to say. Okay, so the squeeze theorem is kind of an easy idea, but as you get further and further away from it, are you going to remember exactly what it is? Okay, so again, usually the way I've seen it is, here's all the information you need. This is a true statement. What is the limit of the thing in the middle? You don't worry about the thing in the middle. You worry about the things on the end and show the limits of those. Is that okay? All right, so that's all I have for you. What would you guys just want me to shut up and then you do it, or do we want to? All you got to do tonight is 39 to 57. That means we kind of have a bigger set of problems for tomorrow, because we're going to do 59 together, and then you're going to get to 87. So you're welcome to do it at as many. I don't know what you guys got going on tonight, so like, just know that I suggest you get all the way to 87 by Thursday. Okay. So however you guys need to take care of that, because these aren't like super awful, or there's not like a ton going on. So do you want me to do anything else, or just be quiet now? Take it as you just don't.